welcome to episode 2 of series 2 of Beyond the Model. I am incredibly excited to have Thomas here. It's a pleasure to have you. How are you doing?
I'm doing very well. I'm very excited to be here, and thanks for the invite.
Yeah, so welcome. You really are. Guys, just a quick, why we do this, who we are. Beyond the Model is a community run by Strative Group, which is where I work, and we run this for anybody that is interested in frontier AI, machine learning, whether you are a researcher like Thomas, whether you are someone that's interested commercially, whether you are just interested, it does not matter. We run this so that you can listen to, you can understand the why, the how, the who, and yeah, look, I really hope you enjoy this, and I think it's going to be awesome. So yeah, Thomas, maybe give yourself a quick intro.
Everyone, I'm Thomas. I'm a research scientist at Google DeepMind, and I've been recently working on the VO team, which you might know as the generative video model from Google DeepMind. And one of the big things I've been pushing with my team, which we announced at I/O just recently, was ingredients to video. It's like a way to put like objects, assets, characters, entities into videos and not just condition on text. And that is like one of the, like I've been working kind of in this area of like, how do you control what happens kind of in the world? Like a video model is kind of a window into the world. And how do you really control in a fine-grained detail beyond just like textual controls? Like how do you really control what's happening in the world? How do you build these worlds in these video models? And how do you go from like where we are right now, like individual kind of generative models that built like quick video clips to really like immersive, more like world models over time, and what's missing to get there?
Well, again, thank you so much for being here. How exciting is that? How awesome is that? And really, by the way, as well, like this work in this area generally, right? I think is just okay. Yeah, maybe technically interesting, maybe commercially interesting. I just think it's just so fascinating, right? And it's just so it's like such awesome to work on. But Thomas, we're gonna talk about a few things today, right? We're gonna get to know you as a person, right? And we're gonna get to know the why and the who is behind a lot of these things, and I think understand your journey. We're gonna talk about that very thing as well, and we're gonna talk about the sort of the work you do, the path you took to doing it, right? And how that happened. Because that is awesome to hear. And I know many of you that are watching this and are tuning into this will be equally as fascinated by both the work Thomas and your team do, but like at the end of the day, how you got there, right? Like that's really cool. But in that vein, why don't we peel it back? Why don't we talk about how this all started? Why don't you run us through the journey?
Let me maybe get started with how I got into AI in the first place. Please. And maybe like then slowly make the jump to world models. So some folks might know some of my work on graph neural networks, which was like a big topic during my PhD, and we'll get there. But I want to take a bit of a step back and start more like at my undergrad, where I studied physics, and I studied physics because I was really fascinated by the question of like, where is humanity at right now at understanding the world? Like the core kind of concepts of like, I don't know, how does the world work? And how can we use that understanding to make predictions about the world? And physics is effectively that discipline that really goes down into model building at all different kind of length scales, all the way down to elementary particle physics, up to like approximate theories and like fluid dynamics and other areas, all the way to kind of building like game engines that have like approximate physics in those game engines. And so it always struck me as kind of like one of the most fundamental things worth learning, and which is one of the reasons why I ended up studying physics in my undergrad. But during those studies, like one thing that became kind of more and more clear to me is that the way like the physics community approaches problems of like you build a mathematical theory, then you start from that theory and you try to kind of instantiate a model out of that, like the standard model of particle physics, which has like a number of parameters that kind of describe really at a very kind of theoretical level the like physics at the smallest kind of scales.
Right.
But at the same time, it is indeed very, very hard to then go from those theories to actually make like scalable predictions over different horizons in the world. Like
different game.
Yeah, like for example, if you wanted to understand intelligence, like even if we had like a theory of everything at the very fundamental level, it would probably not tell you anything about intelligence, about emergent phenomena at different length scales. And so over time, like I just got more and more interested in the question of like, what does physics really not cover very well? Like for example, one of the other big questions of the universe, what is intelligence? Like, how do we understand it? How can we build it? How does the brain instantiate it?
Small question.
It's a question worth studying.
Yeah.
And that ultimately got me thinking if I should probably switch my area of focus, because I was ultimately interested in like, okay, what are the big open questions that are still unanswered? And it felt to me like the standard way of approaching problems in physics just doesn't scale very well to many of these other big questions.
Yeah.
And at that time, that was around 2013. Machine learning was still, and deep learning was just deep learning was just getting started.
Yeah.
And it felt like a really great time to dive into that area, because it held like the promise to have a more kind of scalable approach to model the world. Like if you look at physics, like one end of the extreme is like you try to model the world with the fewest parameters possible.
Right.
Like the standard model of particle physics, you can think of it as maybe using like 19 or so parameters, and maybe more if you include the neutrino masses, but I don't want to go into details. Then machine learning or deep learning, you can use to build models of the world as well.
Yeah.
But it really goes to the complete other extreme of that other end of the spectrum, which is like you go to the maximum number of parameters, and you don't really care about like the precise interpretability of the theory, but you just care about like making the best possible predictions and building the best possible simulation.
Yeah.
That got me like the difficult thing is always when you realize you want to make a career switch is how do you actually go about it? Like how do you go from where you are right now, like in that case physics as an undergrad, and then I did my master's in physics, wrote like a master thesis, published a paper in this space, back in physics and quantum optics at that time, and then was like, okay, I don't really want to continue that. I want to get into machine learning, study of intelligence.
Yeah.
And one opportunity that came up at that time was a group at the Max Planck Institute for Brain Research. They studied, and they still study, the brain from a very interesting perspective that's called connectomics.
Yes.
The area. And connectomics is like an area of trying to map out from an existing brain, trying to map out all the neural connections.
Yep.
And you can think of this as like you can approach it from different length scales. Like you can look into basically studying that at the smallest possible length scale, like with electron microscopes, down to like the nanometer resolution. Or you can do like more like fMRI studies that are more like centimeter or millimeter length scale. And so that particular group, which I found very interesting, they had this problem of basically like they try to tackle the problem of this nanometer scale connectomics, which basically involves taking a piece of neural tissue, slicing that into like 10 to 30 nanometer thick slices, and then putting each slice under the electron microscope. And it was a very interesting machine learning problem because you just cannot analyze the data by hand. You need help of like some interesting kind of machine learning algorithms. And in that case, in that group, so I spent about a year there as a master student still.
You were a master student?
I was still a master student. I it was kind of in physics. So I had a supportive advisor at the university who allowed me to kind of do my master thesis in a somewhat unrelated topic, but still graduated in physics.
And because like the choices, and by the way, just as like a side note, it's funny, we spoke about this recently, but this idea of like intelligence and in philosophy, but it's really, really interesting to hear you speak about, I wanted to understand in more depth intelligence, because, you know, a lot of people, when they think of that, they think of like, you know, a social science, right? Like, you know, this idea, but this is the thing, right? Like the drive to the curiosity to understand this is really fascinating.
Yeah, and there's not many angles to understanding intelligence, right? You can either look at the brain, our kind of only existence proof of an embodied, like a realization in our universe of intelligence, and try to, or like at neural tissue overall, depending on what level of intelligence you care about. But like, let's say the human brain, or even like primate or mouse brains. You need to understand, like you can understand intelligence from a behavioral perspective, but ultimately, what's interesting from a neuroscience perspective is to look at like the actual implementations, like what do the networks look like, how are neurons connected, how does that give rise to behavior. That's one angle, and that angle I found very interesting for some time, and of course there's a huge field around this.
It was also like just really interesting.
Yeah. And then the other angle is you say, okay, you can go from first principles and you try to build up intelligence from scratch, and that's effectively the field of AI, and more recently dominated, of course, by machine learning as the main technique behind it. At that time, like I was really curious to learn about like how far can you get with this kind of connectomics approach, like, and I was about to kind of bet my career on that direction just because I found it like what if you just had a network of the brain? And machine learning was also like the technique to analyze the data. So it was kind of a bit of a hedge against, okay, which direction do I want to go afterwards? Do I want to go into machine learning or do I want to go into neuroscience? And so that felt like at that time like the perfect group to spend a year at. And that also ultimately is the research problem that got me into graph neural networks, which is what I ended up doing for my PhD.
Yeah. And just by the way as well, like it's funny to hear you say like this, you know, this kind of like ultimatum, because I think and again, right, look, this is not just not black and white as this, but some of the ideas of, you know, like what neural networks, like what are they, right?
Yeah.
Come back, and we talked about this. We talked about this in the previous episode as well. But this, you know, even in the 50s, in the 60s, right, and like neuroscientists and psychologists and how
cognitive scientists,
yeah, exactly, right, and it's all integrated. So to hear it being unified as, I guess, like intelligence from the first principles, like it makes yeah. I've never thought about it that way, and it's really interesting.
I think a lot of people in the community ended up working on deep learning and all these kind of frontier generative AI capabilities because they ultimately cared about understanding intelligence and understanding the world from first principles. And so that's why you probably see so many physicists in this field, so many people with a cognitive science background. And in my particular case, I think why I ultimately decided then to double down on machine learning is while studying this problem in this 1-year internship, effectively one major issue in analyzing this brain data was you can kind of segment that data with like that time 3D convolutional neural network. You can segment these kind of neural like this electron microscopy 3D data. But the problem was that even if you segment this with the best algorithms at that time, you end up with either a lot of mistakes where different segments are merged and you have two neurons merged into one, and then you cannot really properly analyze the data. Or you go into the other extreme, you have a lot of different independent chunks.
Yes.
And so one of the big problems was, how do you connect those chunks? And it turns out that is kind of a graph learning problem, because if you have in a 3D volume multiple different chunks and you need to figure out, do these two chunks belong to the same neuron? It's kind of a problem where you have maybe already a few chunks connected. Those form a graph and you want to complete that graph. You effectively want to do link prediction in that graph. And it turns out that at that time, when I looked into the problem, there were just no good models for like that specific problem that could take in rich features, which were like the information on each segment of these neural segments, and would kind of propagate these features along this kind of network structure and make a prediction about whether two segments are connected.
Right.
And at that time I was like, okay, well, if something clearly doesn't exist and doesn't work, that's an opportunity, right?
I want to work.
And so exactly. And so at that time I felt like, okay, this is maybe the right thing to do for like spending the next 4 years or plus on my PhD to really tackle this problem. And at that time, the like Max Budding's group, where I ended up doing my PhD in Amsterdam, they published a bunch of influential papers in deep learning. Maybe some of the most influential papers, actually. Like, for example,
absolutely,
Dirk Kingma, who did a PhD in Max Budding's lab, like he published a variational autoencoder paper, which is like still fundamental to this day in many deep learning kind of architectures. Adam, the optimizer, even though Max Budding wasn't on the paper, but it still kind of came out of that lab.
Yeah.
And it just like felt, okay, this is like a great spot to do that work. And Max at that time had an opening for like analyzing network data.
Yeah.
And so that and I was also kind of off cycle because I was doing all this kind of work in Germany, and I was a little bit off cycle with like these internships because I didn't graduate at the standard kind of end of academic year kind of
interesting
timeline. And so it was a bit off cycle for all the kind of UK, US PhD positions. And so that position came up, I applied, and Max and I resonated very well.
Nice.
I still remember I probably didn't do super well in the interview because my machine learning background was still kind of up and coming. And at that time, I remember I couldn't even write down a Gaussian mixture model, which is like a standard thing you should be able to write down as like, if you want to do a PhD in this area.
Oh, yeah.
But it ultimately still worked out. And that's how I effectively ended up by a kind of a sequence of like pretty more like opportunistic in a way choices. Like I decided like this position came up in Frankfurt at the Max Planck Institute for Brain Research. I discovered a problem there, then found a group that had exactly a PhD opening on that topic. So these things are just like hard to plan.
Possible to plan, one might say, right? And there's an element of, you know, like because the work that we do, right? We work with many researchers who have published really foundational and influential work. And one of the reasons we're so interested in this is because, I mean, naturally people listening to this, right? They might, you know, listen to your story and they think, I want to emulate that. And then the thing is though, right?
Yeah.
You know, there are things you can emulate, right? Like you can emulate this idea of, here's a hard problem, I'm going to go and solve it. But what you can't emulate is this, you know, perfect storm of the right problems becoming in front of you at the right time. But that's not like, it's not to say that, you know, you were just in the right place at the right time because you weren't, because you saw those problems and you thought, right, well, this is interesting. I want to solve this.
Yeah, you in some sense, one strategy that works very well for people is to kind of maximize your opportunity surface.
Yeah.
Just expose yourself to interesting problems.
Yeah.
And by being at kind of a frontier lab or being in a frontier team, that case, like this connectomics lab was kind of a frontier lab that really had to apply the latest machine learning techniques, and they had to figure out like, and had to be integrated in the community. So they knew about all these different labs. And someone like at that time, it was kind of difficult to even get into that community. It was a relatively small community, like deep learning. And
nothing like it is now. Right?
It's nothing like it is now. Exactly. Like when I started my PhD, from the time I encountered that graph learning problem to then starting, there were maybe like 3 older graph neural network papers.
Yeah.
One from Marco Gori, like called literally the graph neural network model. And then a bunch of new papers that came out just in between the time when I made the decision to start the PhD and start the PhD that kind of looked into that problem. And so it was still like now, if you were to wait 3 months and try to study a topic, like, I don't know, like most topics of that are of any significance, you'll probably find like a massive amount of papers and a massive amount of people studying problems at this point.
People say sometimes, right? And because, and actually, right?
Yeah.
I think there are three really interesting times to do a PhD in machine learning, right? Essentially, I think one of them is probably ImageNet, right, during that time and that change. I think the second is, well, precisely when you did it, because of because of how much more influential deep learning became, right? And then attention and transformers and how that happened. And then the last is, of course, GPT, right? And doing PhDs during that time is really interesting. But I think one thing that is like a really good point is, like that it's hard for people to imagine, I think, and I guess actually this is a kind of an offshoot question, but when you were looking into this, right, and going to decide to do the GNN stuff, did you actually think at the time that things like, well, I mean, maybe GNNs, but also maybe deep learning would be so accessible and so used right now?
Yes and no. I mean, in some sense, when I started my PhD in 2016, it already felt like I was kind of a little bit too late for like the impactful work to be done. And there was kind of a feeling some people had at that time because, like, I don't know, like some of the big discoveries have already been made. But then the moment you dig into that, you feel like, okay, no, it's actually like a vast landscape open in front of you. And it's not, it wasn't very crowded at the time. Like you could literally sit down for like, as like an individual PhD student without like access to a massive number of GPUs. In fact, some of the early graph neural networks experiments I just did them on my laptop because like you could get like quick results within like 2 minutes and you can have like a super quick iteration cycle. And so the initial kind of paper was like done within like maybe effectively 2 to 3 months of research, which is like the one graph neural network paper like called graph convolutional nets or semi-spec's classification graph convolutional nets. It's a paper that got a lot of citations by now, but
a lot, yeah.
Ultimately, it ended up being a relatively quick exploration. And it was never my end goal to kind of build this model. It was just something I felt the need, okay, this is clearly something that's missing, like having an efficient kind of message passing or convolutional architecture for graphs that bring some of the ideas that are successful in other areas like image classification to that domain. And it wasn't the only paper at that time. There were quite a few, like a handful of papers in that space. What I think made this paper another kind of lucky coincidence at that time that made this particular work successful was that TensorFlow, well, came out a little bit earlier, but TensorFlow just released a sparse matrix multiplication API. And that, if you think about learning on graphs or networks, your graphs and networks are very kind of sparse data structures. And if you wanted to implement something like a graph neural network, before at that time, you had to do a lot of work like yourself. You had to write your own CUDA kernels. It was not very accessible.
Yeah, for researchers, by the way, as well, like, of course it's a different world now, but most researchers are doing that, right? Like at least at that time, well.
No, exactly. Especially like usually it's either PhD students that are already later in their PhD and then they figure out this problem and then just the barrier to entry to invest into that because the landscape was so vast, you would rather pick a problem where you don't have to build your own CUDA kernels.
It's not easy to do.
Than to pick one where the outcome is highly uncertain. But at that time, the lucky coincidence was this just came out. It was like the perfect fit because all of a sudden you can implement these message passing operations like using just sparse matrix multiplications and which is a very simple implementation, and it ended up basically being extremely scalable. So before that, graph neural networks existed, but no one really scaled them to more than like using modern gradient descent. Scaled them to more than, I don't know, a few hundred or 1,000 nodes. And in this case, we could scale them to much, much larger graphs.
How much larger at the time? Like how immediate was the
biggest graph was more like on the order of like 100,000 kind of nodes, if I remember correctly. But like still relatively small. Still running on a single GPU.
Unheard of now.
And these days, you would scale these models, of course, to much larger graphs, and I mean, graph neural networks have become like a standard toolbox in the neural network kind of deep learning toolbox, a standard tool in the toolbox, and they're used across the industry for things like recommender systems. We have big relational graphs, and so these things can be massive, and so there's like lots of teams investing in building very, very scalable approaches.
Yeah. And so you do this project and you work on this paper, which now, as we know, I'm not sure as to the exact amount of times this has been cited, but it's in the many, many thousands. And I suppose when did you know? Like, when did you realize, like, oh, wow, people are like really interested in this?
When I worked on this project, it already felt like something too good to be true when we had the first results.
Really?
Because it was my first project in my PhD. So I was like, okay, I've been working on machine learning for like a bit over a year since that time. So I kind of trusted that I was doing the right things, but I was like, okay, this is very suspect. Am I getting the right? It's very suspicious. Like, do I have a bug in the model? Like, I spent a lot of time. I spent probably like 2 weeks just trying to like double check every single thing.
Disprove, or make sure it was working the way.
To make sure these numbers are correct, because there was just so much, like, it was a lot faster, and also in terms of like generalization, quite a bit better than some of the earlier papers. To be fair, there were not many earlier papers. Yeah, it was like a small community, and still it felt like something like that might be impactful.
Yeah.
So we try to get it out as fast as possible. We put it on the archive first and submit it to iClear. And then I had a bunch of follow-up projects in that space. But ultimately, I was always interested to get back to this idea of how can we use these kinds of models now to simulate the world, to do more interesting things, in my view, than recommender systems. I mean, recommender systems are extremely like impactful and an important industry. But personally, I was always interested in like building simulated world, understanding intelligence, these kinds of bigger questions. Yeah. And that's also like the way I approached more or less decision making around what project I want to focus on next.
Interesting.
And that's how I, about 1.5 years later already, after this paper, worked more on a problem of like using a graph neural net to kind of simulate physical systems. Mm-hmm. Where you have like nodes being individual kind of particles or individual motion capture points in a human who's walking around. And then you use a graph neural network to like pass messages between these individual nodes, and then effectively predict the future, like predict how the system is going to evolve over time. Right. Building a simulator effectively. And that has, that wasn't done in isolation, of course. Like, a lot of people in the community thought about this problem. It started to become its own kind of thing, like using graph neural networks for simulation. And that direction worked out pretty well. And it got me thinking as like, and that's how I kind of came back to world models during my PhD. And the final project of my PhD was called Structured World Models. That was the realization that these models are now really good at kind of simulating physics if you have a structured representation of the world. Right. And that structured representations could be like motion capture points on a human, and you just pass messages between those points along the skeleton, or you have like a particle-based representation of objects, and then you can learn very accurate simulations. Mm-hmm. But if you then think about kind of raw observations in the physical world, like how our brain simulates the world, like it has to deal with like just photons coming into our retina, effectively just like equivalent with pixels in a camera.
Immense amounts of information.
Yeah.
Like really complex information from many different ways. You know, audio, visual. Like it's hard to sum up from like the complexity of the problem of how we perceive data and how we analyze it.
Exactly. And so it turned out like it turned out to be a very interesting problem. Yeah. So how do you go from like these extremely like low-level signals, like just video from a camera?
Yeah.
How do you go to something that you can simulate efficiently? Like, how do you go to like a high-level structured representation? That is something I spent quite some time on. Ultimately, after my PhD, I decided to join Google Brain. After also spending some time at DeepMind as an intern before that time. And there, I ultimately decided to double down on this direction and really try to see how can we build like models that go from like raw visual observation, or raw observations, and even like audio or sound, to these like more like structured abstractions that you can effectively simulate.
Yeah.
And this has kept me busy for quite a few years. And
probably will do.
And I think like it's still kind of a major unsolved problem. Like how does abstraction building work? Like how do we as humans even like we know we have like core abstractions like objects that we reason about, and we perceive the world in terms of like these structured components, also in terms of events across time, or even like in audio, like we have phonemes, we have words, all these kind of like structured abstractions that bundle together like low-level perceptual information. And once you have these structured abstractions, modeling becomes very kind of efficient and easy.
Yes. Yeah.
You can suddenly also, one reason why language models like took off way before like robotics or world models or like models that deal with like the messier low-level data, is because these structured abstractions are right there for the model. They're already pre-processed, and the signal-to-noise ratio is much higher. And you don't have to deal with like the low-level sensory data.
Do you ever think, by the way, that working on, and we'll get to it in more detail, but working on world models, right? Do you ever think that gives you gives you a deeper, or maybe more fascinating interest in how complex we actually are as humans and how we perceive the world, right? Do you think about those things? Or?
Oh, for sure. I mean, there's a lot of introspection that sometimes goes on when you try to come up with a research direction. And of course, like people have been thinking about like world models in terms of like cognition for a long time. Like maybe like some people say even longer than people have like even before terms like machine learning AI were point.
Totally.
In like the scientific literature specifically, like the term world model comes up even before then. And then of course like world model has like, I mean, maybe we should briefly mention like what is even a definition?
Yeah, I was actually going to say
if you ask like 10 different researchers, you get 10 different answers on this question because it's just like there's so many connections people make in terms of there's like model-based reinforcement learning, where the world model would be like the model for reinforcement learning agent. Then there's like world models more like from a cognitive science perspective or psychology perspective, which is like the internal, more like abstract model we build of the world, like really thinking in terms of abstractions and cause and effect and these kinds of things. And then there is like more recent works like GNN and others, where it's really more about like modeling future perceptual data that you can interact on. Like basically you can perform actions and you have kind of a simulator of the world. And so to me, that kind of those two aspects, like having a simulator of some observation of the world, like this could be a camera observation, it could be a multimodal observation, something that is grounded in the world, so something that is actual data from the physical world. You want to build a simulator of that. That's one component. And the other component of a world model to me would be that you can control it, that you have fine-grained control over it. Like that's the action component.
Yeah.
And it doesn't have to be like an action in the traditional sense of like an embodied agent that does something. Because if you then, going back to your question, think about if you introspect a bit about how we can kind of mentally manipulate like the environmental state, we can think about all kinds of interventions. I can mentally make that cup kind of fall over in front of and I can kind of visualize how like the liquid spills out of it. And those are not really captured by this more like embodied agent kind of paradigm, unless you specify the action space to be much more general. The action space being really like intervening upon literally everything in the world, like every single object. You can everything we can kind of conceptualize, you can kind of intervene on. You can think of mentally like the lighting changes, like the mood changes, and like all these kinds of things.
So much information.
Yeah,
it really is. And just on this as well, right? Because look, when you talk about world models, right? People's imagination just runs wild. It really does, because it's actually quite an inspiring thing. And especially when the latest GNN, like VO, right? That was free for a weekend. I sure tried it.
Yeah.
And it's awesome. But especially like when you release these things, right? I think this is the research that gives people a kind of glimpse, like it's like a one hand into the future.
Yeah, I think these kind of moments that really wow people and really impress people, where including kind of like researchers who are at the frontier, are when you get a glimpse into how models, especially now in this recent class of visual models, reasons about the world. And you could even argue that even like image generation models have like some kind of world model in them. Like they understand about lighting and all these kinds of things. Of course, you cannot prompt them for dynamics unless you have an editing model. If you have a model where you can start from an image, you can prompt it for an edit. That's kind of like a glimpse of a world model.
Just a different world, right?
It's still data grounded in the physical world. You just make a single step and you get one kind of outcome in the future. You don't get like the full video observation. But that's not really what's kind of ultimately always needed. Like you don't, like a world model doesn't necessarily have to be a video model that runs at 24 frames per second or something like that. Like it could even be, it's an open research question whether world models are best instantiated as like a generative model over the observation space, like meaning you actually build a model that predicts pixels, for example, if the observation space is like visual observation, or whether the world model should be more like in terms of abstract latents, like a latent representation, an internal representation of the world. And you want to model that going forward in more like higher level events. And the argument often goes, let's say I want to mentally simulate how, or like a world model should simulate what happens if this cup here falls over. The liquid could spill out in so many different ways. Like if we were to judge a model by how well it does in terms of pixel perfectly predicting the physics, that's probably going to be very, very difficult. And then the argument goes that at a more conceptual level, it's pretty clear. Cup falls over, liquid spills out. That's kind of the event, like the sequence of events that happens at a more kind of abstract level. That being said, what we've seen in more kind of recent months and years is that it's actually not very hard for these models to predict like kind of all possible plausible outcomes for these kinds of things, because they are kind of like they learn about the distribution of the outcomes to some degree, and then of course they all have biases, etc. But like you can think of it, even if you learn a world model in pixel space, you just learn a distribution of the possible outcomes, and you just get one instantiation of that. Maybe the liquid flows in this particular way this time, and then maybe the next time you prompt the model, it flows in a slightly different way. But it still gets like the core of it. The cup falls over, liquid spills.
Yeah. And it's interesting, right? Because, and by the way, like it just every time you mention the word like physical or physics, right?
Yeah.
It's just like bringing me back to, like this young man who was choosing to study physics and your interest in the world and how full circle it goes, which is it's really awesome that you've been able to like pursue these things right now. But I think one of the reasons, by the way, and this is just from somebody, and actually I use this specific example with ChatGPT and why it was so big is because anybody can interact with it, right? And you get it. It makes sense to anybody, right? And as like a researcher, and specifically, you would the ways that the technical, deeper technical workings of how you do these models is really interesting to the research community, right? And then the models themselves and what they produce is really interesting to the research community, commercial community, and then just everybody else, right? Because you must surely see the stuff that people produce with these things,
absolutely. I think the absolutely mind blowing thing, having gone through like the development of this over, for me, like the past little over 10 years now in the machine learning community, and there's people, of course, who've been in this field for much longer. But even in those last 10 years, it suddenly went from like foundational, crazy research explorations and ideas, like within like an ever-growing community, but it was still mostly like the target audience was the community of researchers. Sometimes you interacted with like people in other communities, and not even sometimes, it was actually like often the case, because machine learning already like 10 years ago had like, or way before that, had like very far-reaching impact across the different disciplines. Like all of a sudden you interact with people from chemistry, from drug design, and some people say as a machine learning researcher you kind of get to play in everyone's backyard. But it was still kind of the backyard of other scientists or other research or industry practitioners. But like the massive shift that I think people haven't really anticipated, like even 5 years ago, is that all of a sudden the backyard is not just everyone's backyard in terms of like every other researcher's backyard and every other industry practitioner's backyard, but literally everyone's backyard. Like it it was absolutely mind-blowing as someone like who's worked in this field, from seeing like small explorations to this becoming really big, how this is really like something everyone can now experience and interact with.
I think that is just one of the biggest things, like really is. And I think as well, I see stuff come up now, right? And this is a whole different question, right? I see stuff come up and I just think, like when we design these models, I just think we forget how creative humans are, right? And like what we do with them and how we use them and what they'll be used for. And, I suppose like sitting there and thinking about it and watching what people do, like everybody, like there are entire industries being born out of this generative content for world models, right? And how that goes forward in the future. It's just wild, like special place to be involved in.
No, exactly. Like I think one thing that surprised some of us on the team for VO in particular is like people discovered how to use the model in like artists and others, how to use the model in ways we wouldn't have imagined possible. Like for example, so I wasn't involved in like the VO, like text to video and image to video part. My main focus was on like getting these multiple ingredients and multimodal conditioning into that. Like multimodal meaning text and images. The interesting thing is like what artists did with the model in terms of like one thing that went viral on X a few weeks ago is you can actually prompt VO by just drawing kind of an instruction in like the first frame you send to VO as like an image conditioning frame, and then it kind of executes that instruction. Like the instruction could be like replace the person, draw a circle around someone, and then just replace the person, like literally on the image, and it executes that. These kind of immersion capabilities are like first of all they tell you something about the kind of like reasoning capabilities and also like the internal like effectively world model these models have. Even though they're not technically kind of a world model that he can kind of continuously act on like genius, but they still have like a remarkable kind of underlying understanding of the world.
Which is, I do think, right, it's probably going to be overall massively positive and will probably push forwards, actually, machine learning research generally and AI research as a whole. The fact that people have access to these things, the fact that they can use them, because, I'm thinking that the more, like humans are just so creative and like, really they will do stuff that is just incredible and it's so complex. And, like when some of the greatest scientists in the world, right, will think of ways of solving problems that just only they with their own specific experience and perception of life and of just everything that's happened to them will lead up to a point which will allow them to, logicize and think about things in a certain way, right? And that leads to some of the greatest, like the greatest projects or the greatest things that there are. And you'll see that, I'm sure, right? Like I saw exactly what you mean about the Alex as well. But you'll see this in the future. The more complex these models get, the more you can do with them. You will see people do stuff, and like you and your team will just sit there and go, damn, like
no, it's like fascinating to just see how like these models, once you put them out, how they're being used by users and the kind of feedback you get. And of course that feedback feeds back into like when you think about, okay, what comes next, etc.
Yeah, it really is. And well, look, so firstly, right, we've covered a lot. I really do mean this. I could listen to you talk about this for hours, dude. Like, really. And I think what is really interesting to a lot of the people that watch this is, it's easy to look at your research evolution and look at this and think, well, this makes sense, and okay, I understand how you go from here to, but you draw it all back, right? There was a plan, maybe, but you're somebody who pursued what was unendingly interesting to you, right? And how you wanted to perceive the world, and these are really complex problems. And to learn how somebody, there will be scientists, there will be people watching this and listening to this that are like, 14, 15, 16, 17, going into undergrad and thinking about, how do I emulate someone like this, right? And how do I do this? And to hear that is really, really cool. So thank you for sharing this.
Yeah, no, thanks for inviting me. I mean, it's a fantastic conversation.
You are so welcome, really. And I do have one more question, right? And this was asked by the previous guest, which is as tradition here. But this was asked by Yamping, who formerly worked at DeepMind, actually. And his question was, with all of the noise around
AI research, right? You know, the $100 million offers, and that's a different story. But all the things that are going on, the amounts and the places and the stakes of what's happening.
Yeah.
How do you choose where to spend your time?
I mean, that's like one of the most. It used to be one of the most important questions. It still is, and it's maybe ever more important to find the right, to really choose the right topic to work on. There was like a time in the AI research community where the optimal strategy was to kind of hedge your bets and focus on multiple things, and because some projects get stuck, some projects kind of there's like ebb and flow kind of periods. But like the times really have changed, and I think it really makes sense to try to figure out one thing to commit to for a certain period of time. And it's fine to kind of change every couple of years, maybe even earlier, when you think it's like not the right thing anymore, but like really double down on like one particular direction that first of all, kind of aligns with where you want to be in terms of your own personal career North Star or like research North Star, but also where you have like the right opportunity in terms of your environment. Like it doesn't make sense to focus on something where like if you pick your next project, something that's just like where all the odds are stacked against you because maybe you just don't have the resources of the right collaborators. So just figuring out like the entire environment, how like what gives you kind of a competitive advantage, both from your own kind of interests, your backgrounds, what motivate, like what is a problem that you really would want to dive super deep into and become an expert in. I think that's how I personally chose research problems. And overall, that sometimes means jumping off of like something that is successful.
Making hard
to exactly, maybe even before something peaks. Like in my case, I moved on from graph neural networks before the field kind of really peaked. If it even peaked, I mean, things are still going kind of up in terms of like the community size. But it felt like there's still the right time because I felt like it didn't fully align with where I wanted to be in terms of like the research problems that I find interesting. And so I think that is like important to keep in mind when the right time is to kind of also switch topics.
If you listen to anything, listen to that. It's fantastic advice, really. No, that's really, and I think like just you never forget, right? You have to do something that motivates you. You have to believe.
That's one of the most important things. Like if you go to work every day and you feel like, okay, why am I doing this? Then this is not like in your favor.
No, really. And I've often, I've often heard people refer sometimes, right, to being a researcher, and especially people that do high impact work as being sometimes even quite lonely when you start problems, right? And can be
especially more in like foundational research topics. Like you often start out like just thinking about a problem. I think these days many of those bigger projects are big team efforts that are really working at a high pace. So feeling lonely there is like, I think, very rare. Just because things just move so fast and you just like go with the flow of the team. But yeah, it definitely happens. Like especially if you think about more like if you bootstrap a completely new ideas.
And there will be ideas that come in the next few years. That we cannot possibly foresee right now, and will require somebody to go out there and do just that, right? Like it will happen. But like Thomas, I really unendingly appreciate your time, and this has been incredibly fascinating. We have to ask you. It is tradition on Beyond the Model to ask a question for your next guest. I know I'm throwing that on you out of the blue, so I apologize. But yeah, it could be anyone. We haven't decided who the guest is yet. So you tell me, what are you going to ask them?
I think in line with like maybe the question we just had, one interesting question that is super relevant for anyone getting started right now in this area is like, is it still worth doing a PhD in this space? And I'd be curious to hear what whoever the next person is.
That is a great question. No, that really is as well, because there is so many. Guys, I can't wait to ask that. It's a great question, but Thomas, thank you, guys. It's been what an amazing experience to be able to spend time with people like Thomas and learn about how you do things. And we're in San Francisco as well, which is awesome. Which is where the magic happens a lot of the time, but not all the magic. And I think people get a lot of value from this. So thank you again for your time. And guys, episode 2. There we go. Thanks for watching.
Thank you for having me.